All right, in this video, we're going to be talking about polarity, and we're going to be able to determine whether or not a molecule is polar or non-polar. So bond polarity is going to be determined by electronegativity, and the larger the difference in the two atoms, the more polar the molecule will be. So the more electronegative atom is going to attract electrons. So whenever that atom attracts more electrons, overall, it'll be a little bit more negative. So our nonpolar covalent bonds are going to share electrons equally, so there is going to be no electronegative difference. Our polar covalent bonds, though, do have a electronegative difference, so our electrons are going to be shared unequally. And this is going to be what causes them to be polar, is that unequal sharing of electrons. And then our ionic bonds are going to be so polar that electrons are just transferred. Now, our molecule polarity depends on the polarity of the bonds and how they are arranged. So a molecule will be polar if it has an uneven distribution of electrons. Uneven electrons cause one end of the molecule to have a partial charge, and we call this a dipole. We're able to draw the bond polarity arrows to see how uneven or even the electrons are. And we're going to turn all bonds into arrows facing towards the more electronegative atoms, and bond polarities can cancel each other out if they're equal and opposite. All right, so let's go ahead and take a look at the example of our SiO2. So first thing, we do have to draw our Lewis structure. So our silicon provides us with 4 valence electrons. Our oxygen provides us with 6, but we have 2 of them. So we get a total of 16 valence electrons we are able to work with. Now, our silicon will be in the middle with our oxygens on either side. We'll go ahead and draw those bonds, which uses up 4 valence electrons, meaning that we only have 12 electrons remaining. Using those 12, we are then able to put them around our oxygens first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have used up all of our valence electrons. But taking a look at our structure, our oxygens do have that octet, but our silicon does not. So we need to go ahead and we need to form those double bonds. So our structure in the final stage will look like this. Now, from here, we need to look at where the electrons are. So in this case, the electrons are going to be shifting a little bit more towards the oxygen. And this isn't everything going to be outside. But because the oxygens are pulling equally in the opposite direction, they are going to cancel each other out, making this a non-polar molecule. All right, let's go ahead and take a look at another example. All right, so we have our Br2s. So go ahead and we're going to draw that structure. And for just time's sake, I'm going to go ahead and just draw it out. All right, so this and everything is going to be our Lewis structure for our Br2s. Now, we have to look at our central atom, and because we have our lone pairs are going to be really negatively charged, and so that is going to be where the majority of the negativity of this molecule will be, making it a polar molecule. All right, let's take a look at another one. All right, our next one is going to be our CCl4. I'm going to go ahead and draw the structure. So we have our carbon in the middle, chlorines around. All right, so taking a look at this. So the electronegativity is going to be kind of pulling towards the chlorines. But because they're all going to be pulling outward and are even, this isn't everything is going to be considered a non-polar molecule. And another way that we can look at this is going to be through symmetry. So because our CCl4 is symmetrical, the electronegativity is going to be evenly distributed throughout the molecule, thus making it a non-polar molecule. All right, let's go ahead and take a look at a few more. All right, our next one is our CH2Cl2. So I'm going to go ahead and draw the structure. All right, so we have our structure right here. Now, if we go ahead and take a look at where the electronegativity is going to go, most of the electronegativity is going to be being pulled towards the chlorines. Now, our hydrogens will pull just like a little bit, but the majority of it is going towards those chlorines on the outside. Now, because this is going to be an uneven distribution, so it's not going to be symmetrical, so it's that uneven, this and everything is going to be considered a polar molecule. All right, we'll go ahead and take a look at two more. All right, we have our pH3 next. All right, so taking a look at this molecule, because of our lone pair on the phosphorus, this is going to automatically make this a polar molecule. All right, one more example. All right, our last example is going to be of our BH3. So drawing that structure, it looks like this. Remembering that boron is one of our exceptions to the octet rule, it is okay to have just 6 electrons around it. Now taking a look at this, it is a symmetrical molecule. That electronegativity is pretty evenly distributed throughout the molecule. So this is going to make it a non-polar molecule. In that, everything is going to be the basics of polarity for a molecule.